Oh, we're almost out of time. I have to be quick with this. All right. That's fine. It's not too critical anyway. All right, team. So, if you guys remember from the learning intention from Tuesday, let's just flick back to it. We are thinking about how we can explain how can mass spec and CNMR be used to confirm functional groups. So we've already talked about mass spec on Tuesday. We talked about how we can use it to find chlorine and bromine. We also looked at how mass spec, if it's an odd number, can confirm the presence of nitrogen. Now what I want to talk about is CNMR and how we can use CNMR to figure out function groups. Remember, if we are aiming for the excellence, you need to be able to integrate your spectra together and use them to back yourself up, okay? So you should see the same information on multiple spectras. So, here is the CNMR stuff. I want to start off by saying that CNMR is probably the most complicated machine to understand. Now, something to remind yourself is that you are not assessed on how the machines work. So let's repeat that with me. I am not assessed on how the machines work.
I am not assessed on how the machines work.
Ms. Garlick is just teaching it to me because I'm a nerd.
Ms. Garlick is just teaching it to me because I'm a nerd.
All right, so if this makes no sense, you guys are nerds. You're taking level 3 chemistry. You don't need to. All right. Anyway, if you don't understand this, it is okay. Do not stress. You never have to explain it for my course. It's useful just to know for big picture understanding chemistry, and also potentially at university it might be helpful. Okay? So, let me just highlight different sections. I'm not even going to be writing down notes because I don't want you guys to think you have to write anything. So, I have lots of different pictures to explain how CNMR works. The first thing we have to keep in mind with how CNMR works and how NMR works is that NMR works by magnets, and when you have atoms of an odd number nucleus, it will spin in different orientations. So the other MMR that you will learn about at university is going to be hydrogen MMR. So I remember learning that with organic chemistry. In fact, the organic chemistry exam from memory, it basically was spec with one more spectra, which is really cool. So we don't teach the HMMR, but we're only teaching the CNMR. So hydrogen has an odd number because it only has the one proton. Carbon, when we look at the atomic mass of most carbon, it is 12. That's an even number, so most carbon do not have this. Carbon-13, which is an isotope of carbon, does have this property. So we're looking in particular at carbon-13 isotopes. They only exist about 1% of the carbon population, so it's not many, but it's enough that we can use it for this data collection. Carbon-13, as another side note, is used for carbon dating. So if we want to figure out how old something is, we look at the carbon-13 values. So what happens is with these odd number nucleus is that they can spin in random directions. So this on the left is showing random directions of nuclear spin. When I introduce a strong magnetic field, I can get the magnetic spin of the nucleus to align in the same direction. So they're all going, vertical. Okay? So this is the strength of the magnet, and then they're all going vertical. Now, when they go vertical, they can go vertical with the direction of the magnet or against the direction of the magnet, but they're in the same direction. They're parallel with the magnetic field. In this case, without the magnetic field, they're just spinning randomly. Okay? So that's the first idea. Okay. Second idea is, let me spotlight this guy here. Okay, second idea is how they are aligning with the magnetic field. So if they're going parallel with the magnetic field, that is a lower energy state. So it doesn't require as much energy to go with the magnetic field, which makes sense because you're going in the same direction. If you're going against the magnetic field, that requires more energy to do that. What we do in CNMR is we measure the difference between the low and the high energy states. Now, the different carbon environments will have different energy levels because the carbon that's involved in those bonds is influenced by what else is attached to it. So, let me go to the next stage. So the next thing we're talking about is electron density. Spotlight that guy again. All right. So electron density, and this is going to now come into place if you guys want to do the thermochemistry external. they do talk about electron density for that external. So this will help later. So when we're talking about electron density, what we're talking about is here's my nucleus, and here are the electrons that are around that nucleus. They are scattered about in a set, there's a set place that you'll find them, but they're set around the nucleus, and they basically they cancel out charges and things. So this is positively charged, the electrons are negatively charged. Now magnets are obviously going to affect charged substances. So the more electrons I have, the more that the nucleus is shielded from the effects of the magnet, and thus it's going to be harder to get that nucleus to change its direction. If it's very exposed, then it's a lot easier because you have less things canceling it out. Okay? So, what happens with our organic molecule and why we can use organic molecules? Where'd you go? Spotlight. No, you don't want to show it on all screens. Wrong one. You want to spotlight this guy. There we go. So, what this then means for functional groups is that if the carbon is attached to something that is electron negative, when we're talking about electron negativity, we're talking about the tug of war of electrons in a covalent bond. So in a covalent bond, those electrons are being shared. They are not always going to be shared equally. If you have something that's really electron negative, so it has a high attraction to electrons, because say for example like fluorine only needs one more electron to complete its outer shell and to be stable. So it's going to be very electron negative. It's the most electron negative element. It's going to be pulling those electrons closer to it. Yeah? And when we talked about it last year, we were talking about molecules having a slight polarity. So a slight negative polarity around fluorine. The net result for the carbon then is now the carbon is more exposed and making it slightly positive. So we talked about this last year with polarity. This in CNMR results in my atom being more exposed. So it's going to be more de-shielded. So let's go back to this one. Spot like this. So basically what happens, this isn't a good molecule. I should have even got another picture now that I think of it. But basically what's happening is that because the carbon is attached to something that's more electron negative, the nucleus is now more exposed. So that's going to then affect its energy levels. So if we look over here, I'm going to spotlight you again. All right. So these are the values here for CNMR, and we're talking about the difference between the low and high energy states. Okay? When I have something that's really electron negative, it's going to be downstream, so towards my left, and very de-shielded. So it's going to have a greater difference in those two values. So just be mindful, we're talking about ppm. I don't know quite what that acronym stands for, but we're just talking about the magnetic difference, the strength of the magnetics. So what we can do then is we can check for functional groups using this. So when you guys are downstream over here, those are usually your things that are very shielded, like your carbons and your methyls or your CH2s carbons and stuff like that. So your inner carbons like that guy. All right? As you go down this way, you're going to get different functional groups that are present. So see, for example, the carboxylic acid you have over here. It's saying that this carbon is very de-shielded, and you should see your peak over here. So we can verify what we see on the IR with the CNMR. Now, the IR is more accurate than the CNMR because it is, like I said, influenced by what else is bonded to it. So if your function group, say for example, you got a carboxylic acid, but it's over here, it's still it's most likely still a carboxylic acid because it is a carboxylic acid. Because if your IR says carboxylic acid, but this is showing over here, and it's not in the range of the carboxylic acid for here, I would say it's still called a carboxylic acid. It's just this peak over here, if that's the only peak, is probably the carboxylic acid peak. And we can look at some examples so you guys can see what I mean. All right? So this is just a verification method. And in fact, I will get our notes from the other day when we did some practice questions so you guys can see how you can integrate in those spectras. So let me just find the notes from last week. No, yesterday. So we can kind of see it. Here we go. I'll grab both of them actually. And I'll grab my green pen, and I need my document camera. There we go. All right. So, let's see. Based on my data here, it says that if I have, just trying to see, I had an amide. So this one's saying if you have a carbon with a nitrogen, it should be around 30 to 65. If you have a carbonyl, let's see, it has it up here. It should be between 200 and 220. Oh, here we go. There's my amide. So my amide, in theory, when I'm looking at the data, should be between 150 and 170, roughly, just maybe 175. So if I look at the sheets that I was giving you the other day, it's going to show me first. There we go. All right. So I did this briefly on question number 3, and I'll show you question number 4 as well. So question number 3, oh, I must have got some water on that. You see how I identified something as the amide from the mass spec, sorry, from the CNMR, IR, thank you. So you see how I identified it as an amide? For the excellence, make sure your spectrums are integrating together, and so you're basically confirming that you have an amide. Because when I look at that peak, it says it's at 180, and when I look at my data over here, it's between 150. It's not quite at 180, but it's close enough. So don't use this as like a hard number to be like, it has to be within this range. It's just to give you a ballpark. It's going to be influenced by what else is bonded to it. Okay? So that one is just confirming my amine there, or sorry, amide. And then this one over here, we see how we have the 3 peaks. So I want to figure out which of these 3 peaks is probably going to be my amine. Because this is question number 4. Figure out it was amine from the IR. And then when I look over here, the carbon-nitrogen bond is between 30 and 65. So 30 and 65, we have 40 right here, and then 65's up here. Remember that the amine attachment, the carbon's going to be on something that's more electron negative than the other things. So, did I draw this molecule out? I thought I did.
I think you did.
Did I draw another piece of paper? Yes, I did. No, that's not it. There it is. Okay. So, we said how this is 3 carbon environments, and we're trying to figure out which could be which peak. This one here is going to be this peak over here because it's within the range. $30 and I think, what was it said on there? 30 to 65? That confirms an H2. All right? And if I was thinking about this logically with the rest of the molecule that I found, this one here is probably CH3. This one here is probably CH2. All right? So that's the integration of that spectra. There is going to be a little bit more that I'll talk about next week, which is going to be fragments, and that's the other thing you need for the excellence. This standard actually does have a reasonable jump from merit to excellence. It's actually one of the few chemistry standards that do that. So just keep that in mind. I would say still, though, give the excellence a go because it's not that bad compared to going from the achieved to merit. If you're doing the work to get up to merit, you might as well do the excellence, is my opinion.
3 credits, right?
It's 3 credits. Unfortunately, our internals are only 3 credits. So anyway, that's the work that you're looking at for today. Are there any questions? Nope? All right. So like I said, remember, you are not assessed on how the machine works. None of these machines. I do not care how they work. You do need to figure out what the molecules are. All right. Cool. We ran out of time for study. That's okay. Just keep doing those practice combination questions, okay?